Hello everyone, in this video we're going to be looking at section 11.1, which is vectors in the plane. So we're switching gears here, we're moving away from polar coordinates and going back to rectangular coordinates. Okay, so subsection 1 here, component form of a vector. Many quantities in geometry and physics, such as area, volume, temperature, mass, and time, can be characterized by a single real number that is scaled to appropriate units of measure. These are called scalar quantities, and the real number associated with each is called a scalar, right? So, for example, it's 100 degrees outside, right? Or it's the length of a bench is 50 inches long. Other quantities, such as force, velocity, and acceleration, involve both magnitude and direction and cannot be characterized completely by a single number. Right? A directed line segment is used to represent such a quantity. Right? So many of this, if you guys have taken physics before, you're kind of already familiar with what I'm talking about here. So a directed line segment is used to represent one of those quantities because a directed line segment can represent both magnitude and direction. Right? So the line segment PQ has initial point P and terminal point Q, and we use this notation with an arrow above PQ to denote a directed line segment. So for example, if this was point P and this was point Q, then this would be a directed line segment. Right? This would be the the directed line segment PQ. And the length of this, I will do a different color, the length of this directed line segment is called its length or magnitude, or it's called magnitude, and it's denoted by these double vertical bars, P, Q. Right? So obviously this directed line segment has a direction because it goes from P to Q, and it has a magnitude because it is the length. So directed line segments that have the same length and direction are equivalent. So for example, if I had this directed line segment right here, and if I had a bunch of these directed line segments that are all exactly the same in length and measure, I'm just moving them over a little bit, right? These are all examples of equivalent directed line segments. They're equivalent because they have the same magnitude in the same direction. They're just moved around up and down. Right? So the set of all directed line segments that are equivalent to a given directed line segment, PQ, is a vector. So the set of all directed line segments, when we talk about vectors here, vectors are a set of line segments, right? But typically in practice, we kind of forget about that a little bit, and we just start talking about it as a vector is just one directed line segment, but technically the vector is a set of all directed line segments. And when we start moving to vectors, we start using this notation in your textbook, and in books you'll see it with a bold-faced non-script letter. So this is V equal to PQ. If you're writing it down, though, it's obviously not easy to boldface something, so we typically use more of this notation with the arrow on top. So for example, I'd write V as that, right? It's not really even a full arrow. It's not like this. It's just like a half arrow. And so like U would be like that. The vector X or the vector Y. Anytime we're talking about vectors and you're writing them down, we typically use that notation. Okay, so let's look at an example here. Let V be represented by the directed line segment from 0, 0 to 3, 2, and let U be represented by the directed line segment from 1, 2 to 4, 4. Show that U and V are equivalent. So in order for U and V to be equivalent, they need to be the same length and same direction, right? But before we even hop into that, we should probably say what this vector is, right? So let's let P be the point 0, 0, and Q be the point 3, 2, be the initial and terminal points of, in this case, it's V, right? And we're also going to let, we'll call it maybe R from 1 to 2 and S from 4 to 4. I'm sorry, S, which is 4, 4, be the initial and terminal points of U. All right, so those are our two vectors. And so now, again, for U and V to be equivalent, we need to check their length and check their direction, right? So let's look at their length. So I have 2 points and I want to find the length between them. So in order to find the length of these vectors, I'm going to use the distance formula. Right? Because that would be giving me the distance between 2 points, which is the length of the vector, U. Right? So here, if I want to find, again, we use this notation, double bar U. That's just going to be the distance formula between P and Q. So I do x2 minus x1, so 3 minus 0 squared, plus y2, which is 2, minus y1, which is 0, underneath the square root. And so I end up getting 9 plus, should have squared that, 4, which is the square root of 13. Right? The magnitude of V is going to be the distance between the points S and R. So x2 is 4 minus x1 is 1 squared, plus y2 is 4, x2 or y1 is 2, so 4 minus 2 squared underneath the square root. I end up getting 3 squared. All right, this ends up being 3 squared plus 2 squared, which is once again radical 13. Right? So these have the same length. So we're halfway there, showing that these are equivalent. They have the same length. How are we going to show the same direction, right? So the way we're going to show direction is by just looking at the slope of the line segments, right? Because the slope of the line segments will tell us what direction they go. All right, and again, each of these line segments is just 2 points. So we're able to just take the slope between those 2 points. So if I was going to do, we're looking at the slope of U. So the slope of U is going to be the slope between, I think I have U and V switched here. So let me see. V is from 0, it has the 0, 0 in it. So that should have been V, and this should have been U, and then let's do this again. Let's do V first, right? Okay, so the slope is going to be y2, which is 2, minus y1, which is 0, over x2, which is 3, minus x1 is 0, so I get it to be 2/3. And then I look at the slope of my vector u, which is going to be y2, which is 4, minus y1, which is 2, over top of x1, which is 4, minus x2, which is 1. So I end up getting 2/3. So I have the same direction because they have the same slope. So therefore, U, or let's say V and U, are equivalent. Right? That was what the question asked to do, is to show that they're equivalent. Just for fun, let's go ahead and graph these just so we understand what's going on here. So let's do V first. V is from 0, 0 to 3, 2. So that would be this guy right here. Draw it a little bit straighter. Not straighter. That's our U. No, sorry, that's our V. I don't know why I'm struggling with that so much. That's our V vector. And then the other one is our U vector, which is from, this in green, that one's from 1, 2, so up here, to 4, 4. So maybe right there, bring it down a little bit. So that's that vector. So that is u. And as you can see, just by looking at them here, we notice that they look like they are the same magnitude and direction, and we obviously verified that they are, right? The only difference is that the v vector is centered at the origin, or starts at the origin, and the u does not, right? And that's important because a directed line segment whose initial point is the origin, right? I guess we did in orange, whose initial point is the origin, is often the most convenient representative of a set of equivalent directed line segments. So remember, a vector in general is just one is a collection of all equivalent directed line segments. And so we choose one representative from them. And typically with vectors, we choose the one that has the initial point at the origin, right? So for example, we would choose v as our representative of these two equivalent vectors, or two equivalent directed line segments. So this representation of v is said to be in standard position. So anytime we have a vector that has it has its initial point at the origin, it's said to be in standard position. Okay, so we've got a lot more definitions here. I know it's a little bit boring, but hang with me. The definition of component form of a vector in the plane. So v is a vector in the plane whose initial point is the origin, right? Because again, we're going to associate vectors with initial points being at the origin, and whose terminal point is v sub 1, v sub 2. Then the component form of v is just v equals 2, and we use these kind of square brackets, and we say v1, v sub 1, and v sub 2. So this is matching up kind of with what we talked about before, because if we think about like the directed line segment being like the distance, well, if I start at, if my initial point is 0, 0, and I end at v1, v2, then I'm going to call the vector where I end at, because that would be like kind of like the distances. So the coordinates v sub 1 and v sub 2 are called the components of v. If both the initial and terminal point lie at the origin, then v is the 0 vector, and it's just denoted by a bold-faced 0, or in the case where we're writing down on our piece of paper, it would be a 0 with a line over top of it. So that's the 0 vector. And this definition implies that the only way two vectors are equal is if their x components are equal, or their first components are equal, and their second components are equal. Okay, so the question is, if I give you 2 points randomly, how do you write that vector in component form? Well, basically what you're going to do here is take the change in x and I shouldn't say x, but the change in the first coordinate and the change in the second coordinate, right? So this is always going to be the terminal minus the initial. Right, so if I have 2 points, I just take the terminal the terminal first value minus the initial first value, and then the terminal y value or second value minus the initial y value or second value. Right, so it's terminal minus initial. The length of v, again, this is exactly matching up to what we talked about the length being before, right? And we use the distance formula, right? So if I use the distance formula, knowing that this is my like x coordinate and this is my y coordinate, then I would take the x coordinate squared plus the y coordinate squared, take the square root of it, and that's going to give me my magnitude. So this is really just the distance formula. And if you already know what v1 and v2 are, then, because this is v1 and this is v2, then you just square those and take the square root. Square them, add them up, and take the square root. If the magnitude of a vector is 1, then we call v a unit vector. And this is just the fact that we use norm, it gets really important the higher up you go in calculus. And one of the properties of a norm is that a vector has the length of a vector, or the magnitude or the norm of a vector is 0 if and only if that vector is the 0 vector. Right? So the only vector that has length 0 is going to be the 0 vector. And then that was part 1 here, was how, if I give you 2 points, how do you write it in component form? And now the second part here is if I give you a vector in component form, then how can you rewrite it as a directed line segment or between 2 points? And remember that if it's in this form as a vector, its initial point is the origin, and its final point is, or its terminal point is v1, v2, right? So I can just write it as the directed line segment from 0, 0 to v1, v2. Okay, so let's go ahead and try to do example 1 here. So example 2. Find the component form and length of the vector v that has initial point 3, negative 7 and terminal point negative 2, 5. Right? So per number 1 here, in order to find the vector component, in order to find v in component form, what I'm going to do is I'm going to find v1, or the x part, or the first spot, to be v1 is going to be the terminal x value, which is negative 2, minus the initial x value, which is 3. And then we have the second component is going to be the terminal y value, which is 5, minus the initial y value, which is 7. All right, so here I get negative 5, and here I get 7 plus 5, which is going to give me 12. So if I write this in component form, v is equal to negative 5 is the first component, and 12 is the second component. So that is that vector written in component form. And now the other question is to find the length of that vector. All right, once we already know that it's in this form, then in order to find the length of the vector, we just take the first component, which is negative 5, and we square it, plus the second component, which is 12, and we square it underneath the square root. So I get 25 plus 144 underneath the square root, which is 169 underneath the square root, which is 13. So the magnitude of this vector, or the length of this vector, is 13. Okay, let's go ahead and end this video here. In the next video, I'll pick up with vector operations.